In this work, we present adaptive self-distillation for minimizing the client drift in heterogeneous federated learning. So federated learning enables edge devices to collaboratively learn a shared model while keeping all the training data on device, but decoupling the ability to do machine learning from the need to store the data. It's a privacy-preserving model training in heterogeneous distributed networks. It leverages the diversity and volume of the data ingested by numerous clients to train more robust and generalized model for each client. So one of the popular technique in FL is federated averaging. So the model parameters of each device is simply averaged and it broadcasts it back to the clients for further training. So in practice, the data in FL is very heterogeneous, and this heterogeneous arises from the quantity of the samples that each client has, and the label distribution across the each client can be different, and the features of the data itself can be different. So in this work, we specifically focus on the label distribution imbalance, label distribution being different across the clients. So when there exists a label or feature imbalance, the objective of each client becomes different. That is, each client starts converging towards its own local minimum. And this is known as a client drift issue. And this is highly undesirable as the goal of FL is to converge to a global model that generalizes well across all the clients. So, what the typical impact of a local training in the heterogeneous data can be understood from this figure. This represents the accuracy difference before and after the local training at a particular client, which has this skewed label distribution. So the negative portion implies that the model has forgotten the knowledge of the global model, and the positive ones implies it has learned. So you can see the Fed average in traditional Fed average where we don't use any regularizer on the client, and the forgetting happens quite often on almost all the uh, on most of the labels where the representation is very less. When we augment this with the proposed method, we can see the forgetting is much minimized. So this is how the our method works. So once the server broadcasts the model, we have a copy of the global model and the local model initialized with the global model. And while doing the local training on the local model, we keep uh, minimizing the scale divergence between the global model and the local model. So this is the loss. This can be the any task-specific loss. In this work, we consider the cross entropy loss, and this is the proposed distillation loss between the global model and the current local model. And this is how we design the weights of each sample. And this H denotes the entropy here, entropy of the server model prediction. And the higher the entropy, we give less weight to the distillation loss. And wherever the label imbalance is high and the probability of occurrence of the data points is low, we give more importance to the server model. And finally, we normalize the weights to some unity. And we also theoretically show that the proposed ASD regularizer has lower client drift, where the client drift is measured via gradient dissimilarity given by this. But does it imply better generalization? We empirically verify that model converged using the ASD regularizer indeed converged to flat minimum, as demonstrated by the top eigenvalue and trace of the Hessian of the loss training loss computed on the global model at convergence. So adding ASD improves the performance across the board, and different ID and non-ID settings and across the data sets. So in summary, we introduced a novel regularization method in the context of FL that alleviates the kind of problem by adaptively weighting the regularization loss for each sample. And we also demonstrated that this regularizer can be easily integrated atop existing state-of-the-art FL algorithms, leading to further boosting performance. A theoretical analysis showed why our proposed regularization scheme by design helps attain lower time drift. We also proved that this results in faster convergence over the baseline methods.